Now we have got a thin 1.3 meters long copper wire that has a mass of 0.09 kg and is levitated in a uniform magnetic field of 1.4 Tesla. On the diagram above, show all the applied forces on the wire. What is the net force on the wire if it stays on the same altitude? On the diagram above, show the direction of magnetic field. What is the magnitude of current flowing through the wire? So always make sure that you read the question completely and carefully. So this is a classic example of combining concepts of 231 and 232, that is classical mechanics as well as electromagnetism. Now above here you've got a wire that has some mass, right? Mass is 0.09 kg. Then its length is given and it is 1.3 meters long and is levitated in a uniform magnetic field whose direction at this point is not given to us. Okay, it's 1.4 Tesla. On the diagram above, show all the applied forces on the wire. Show all the applied forces on this wire. So if this is a wire, right, and the direction of the current is given by cross with a circle, that means it's into the page. Okay, direction of the current is into the page, and all the forces should ring your bell that we will be including gravitational pull. I'm gonna call it Fg, which will be just mass of the wire times gravity, but I'm gonna not write that for a minute here. And also there will be a magnetic force like that, right? Because there's a current and there's some magnetic field around this current wire, and because of that it will have some kind of magnetic force, right? So that is what is happening here. Now we have taken care of part A. Part B says what is the net force on the wire if it stays at the same altitude, right? So for part B, well, net force is FB minus FG, right? And maybe I should write down like this. Net is equals to M in net acceleration, and this means that Fg minus Fb is equals to 0 because there's no acceleration, right? It stays at the same altitude, and this means that even I didn't have to answer this. This was not needed right now, and this means just from this equation that net force is equals to 0. So you have answered that. Now the important point. Now we have to understand that this is staying at the same altitude. That means that the forces are balanced, right? Now part C says on the diagram above, show the direction of the magnetic field. That's an interesting one. Let's see. Direction of the magnetic field, right? So the direction of the magnetic field should be such that the force because of it should balance the gravitational force. And that is the only reason, that is the only condition where this current wire will be levitating, will be staying at the same altitude. Okay, so let's think of this. If you again look at your formula sheet, you'll find that if you've got a current wire of length L, the force because of the magnetic field around it is given by this. And this is force because of the magnetic field B. And this is going to be I, L, magnitude, IL, B, sine theta, and wherever L cross B is pointing at, okay, this will be the magnitude of it, and direction is given by L cross B. So let's think of the direction run, okay? The direction should, we know, be upwards. This should be the direction of the magnetic force. So in order to have that, let's think of what the direction of the magnetic field can be, okay? So I need to do L, which is into the page, right? And B, well, I need to curl my fingers from into the page to which direction, so that my thumb points to the magnetic force. Okay, and I just did it, and you can't see it, but try doing it. You'll see that if magnetic field is this way, magnetic field, only then you can have magnetic force this way, because current is going into the page, right? So you've got that length into the page, so you curl your fingers from into the page direction towards the left direction, and your thumb points to the magnetic field. So the answer for part C is we just draw the magnetic field like the way I have drawn here. Now part D says, what is the magnitude of the current flowing through the wire? So we know that summation of F net equals to 0. That means Fg is equals to Fb. And you don't have to even think about this equation right here, because this comes from common sense. Because if the wire is levitating, that means the gravity should be balanced by the magnetic force, because there's only two forces there, right? So this should be the case. And I'm going to solve this equation, which says Fg equals Fb. This means Fg is equals to mg, and that is equal to, from here, I L B sine theta. Now as you can see, the angle between the current that's going into the page and the magnetic field is 90 degrees. That means sine 90 equals to 1, and I just have mg equals ILB. Or if I divide both sides by LB, I get I equals mg over LB. And I know what m is, right? 0.09. G is, we can take this as 10. Length of the wire is given to us, and that is 1.3 meters. And magnetic field is 1.4 Tesla. And everything is in SI, so the answer that I should be getting here must be in amperes. And the answer we get is 0.049 amperes. Let me just quickly double check this. Oh, I got 0.49 ampere this time. So that means I might have made mistake the earlier time or this time. So I'm going to calculate one more time. 9 times 10 divided by 1.3 divided by 1.4. Yeah, this should be the answer. Okay, so this is how you do a problem where you have to worry about both the classical mechanics concept and the concept that you are learning right now, the electromagnetism. So this is a classic example. They always do give questions where you have to balance these forces FB and FG and try to figure out different things. So I'd say that this is one of the problems that you should really see and understand how to do it, because this looks very important.